Hello, good morning, good afternoon, good evening, depending on where you are. Welcome to another meeting of Symmetry in Newcastle. The first speaker of the day is Jingyin Huang from Ohio State University, and he will be talking about the Helly geometry of Garside and Artin groups.
Thank you very much for the introduction, and I thank the organizer for the invitation. It's my pleasure to speak here virtually. Okay, so I want to start by defining what is the main object of this talk, basically Artin group. There are several conventions of how you define Artin, so I'm going to just stick to one particular convention, which is the following. I take gamma to be a finite simple graph. Simple graph means there's no loops, so basically there's no edge with the endpoint being the same, and there's no double edge. And then I'm going to let each edge is labeled by some natural number equal to 2. So this will be example. So each edge is labeled by some number equal to 2. And once given this information, then I can write down a presentation. The vertex set. So the generator is just corresponding to the vertices of gamma. And then we have one relator for each edge. So if the edge is labeled by 2, so suppose I have Vi and Vj are adjacent where edge labeled by m, then the relator is the following form. So basically I have an alternating word of length m start with Vi is equal to the alternating word of length m start with Vj. For example, if m equal to 2, this just means Vi Vj equal to Vj Vi. So m equal to 2 means these two generator commutes. And when m equal to 3, that's so more interesting. This is exactly the Braid relation. And this will give you define a group. This group is called the Artin group with a defining graph gamma. And then the most famous example of Artin group would be the Braid group. So I briefly define what's a Braid group. So the element of the Braid come from Braid diagrams. A Braid diagram is basically a diagram like this. So I have an endpoint on the top, endpoints on the bottom. So this is the case n equal to 4, and then I have n disjoint height monotone arcs join them. And then the element in the Braid group are just isotropic classes of Braid diagram. So the isotropy is going to supposed to fix this endpoint at the top and endpoint in the bottom. And then basically the multiplication in the Braid group is just concatenating of these Braid diagrams. And then so in the case of n equal to 4, then there's a generator. So basically, if I have a Braid diagram, then I can always slightly isotope the diagram such that all the crossings in the diagram happen in different height. And then I can just cut the diagram into small pieces such that on each piece you only see one crossing. So that's why these 3 diagrams form a generator of the Braid group. And then we can write down some obvious relations. For sigma 1 and sigma 3, they don't quite interact. So the strands don't quite interact. So they're going to commute. And then the relation between sigma 1 and sigma 2 is more interesting. So this is basically, this is a picture illustrating the concatenation of sigma 1, sigma 2, sigma 1. And this is the concatenation of sigma 2, sigma 1, sigma 2. And it's not hard to see that these two Braid diagrams are isotopic to each other. So this gives us the Braid relation, sigma 1, sigma 2, sigma 1 equal to sigma 2, sigma 1, sigma 2. And then there's a similar relation between sigma 2 and sigma 3. And you can see that this is indeed an Artin group because all the relators is going to be the form defined in the previous page. And then notice that there's a homomorphism from the Braid group to the symmetry group for 4 letters. So in this case, it's just the permutation group of the strands. So whenever you have a Braid group, it's going to induce a permutation of the strands. Okay. So now I want to explain how Artin group arise. So I want to explain a different viewpoint towards Braid group, which is also quite standard. So let's start with a Braid diagram. Looks like this. And let's imagine that we're going to slice the braid diagram at height, at a given height. For example, I slice at this height, then the slice is R2, and then in the slice I see 4 points. So now imagine that if I sort of move the slice from top to the bottom, then at each slice I see 4 points. When you move from top to the bottom, I see a motion of 4 points inside R2. And then this, because, so you start with these 4 points in the top, and then after you move, if you move down the slice, you will see this 4 point moving around, and it end up with the same 4 points. So that's why each braid diagram is going to give you a loop in the configurations of unordered points in R2, if you consider the movement of these points. And we need unordered because the order of these points may be permuted when you move from the top to the bottom. Okay, and then this gives you another description of the braid group. So basically, I can view the braid group as the fundamental group of the configuration space of unordered points. More precisely, we can write down the following space. So I start with Cn, and then first I look at the space of n distinct points in Cn. So that basically means I have to remove all these hyperplanes Zi equal to Zj. So this will give us the space of n distinct space of n distinct points in C. And then I have to model out the action of Sm, the symmetry group on n points. Then that will give me the configuration space of n unordered points. And then the braid group is going to be the fundamental group of this space. Okay. And then, so this is actually, this can be generalized to Artin group. So in general, for Artin group, so there's a similar picture. So, but it's going to be more complicated. So this Cn is going to be replaced by some convex cone in Cn, and this Gi equal to Zj is going to be replaced by some collection of hyperplanes. Again, some collection of hyperplanes in the cone, and then this Sn is going to replace to another group, so which we call the Coxeter group. So what's a Coxeter group? It's basically has the same generator as the Artin group, and it's going to have the same relations before, like this braid relation, but it has an actual relation, basically require that each generator has square equal to 1. So it's basically, you can imagine that Coxeter group is some kind of reflection group, and each generator acting as a reflection. Okay, so now, and the general picture is that there will be a Coxeter group acting on the cone, on some convex cone in Cn, and the action of the Coxeter group is going to permute the a canonical collection hyperplane. So for example, in the case of braid groups, I'm going to have Sm acting on Cn, and then the action of Sn is going to permute this hyperplane Zi equal to Zj. And then, so now you can remove this hyperplane from the cone and model out by the action of the Coxeter group. And then you got a space, and the Artin group arises as the fundamental group of that space. Okay, so this is how Artin group generalize braid group. And then there's an obvious homomorphism from Artin group to the Coxeter group, because the Coxeter group is defined by adding some more relations. And this generalized this homomorphism we see from the braid group to its permutation group of strands. Okay. So any questions so far? Okay, so now I will continue. So now the focus of today's talk is going to be the following conjecture called non-positive curved conjecture, which basically states, roughly speaking, states that all these Artin groups that are non-positively curved in a perfect sense. So this is a bit vague, and I should explain why people even care about this. So what are the motivation behind that? So basically, one of the motivation comes from the so-called K-pi1 conjecture. This is a conjecture proposed in the 1950s, which is still widely open today. So it's basically claimed that this okay, so it's basically claimed that I define this space M, okay, and the conjecture basically says that the universal cover of this space is contractible. And this is known for the Braid group from the 1960s, but it is still widely open for general Artin group. And then also people don't know how to compute group cohomology. So if the K-1 conjecture is known, then there's a nice K-1 space. Then people know how to compute cohomology. But right now the K-1 conjecture is still widely open. So the group cohomology of Artin group is also a mystery. So this is one motivation for this non-positive curved conjecture, because there were various cases of Artin group where the K-1 conjecture is known, and most of these cases actually relies on some kind of non-positive curved structure on Artin group. And this should not be so surprising, because the non-positive curvature usually give you contractibility. And then there's also other basic group theoretic question is also widely open for Artin group. So for example, we don't really know how to solve the word problem, and we don't know how to solve conjugation problem. This is a bit surprising given that you see the presentation is very simple. And we don't even know what kind of Artin group has center. So there's a conjecture, but then nobody knows how to prove it, whether Artin group is torsion free or not. And what can we say about the abelian subgroups? So all these questions are actually widely open for the class of Artin group. And again, so there are a few cases where the word problem is solvable and the conjugation problem is solvable, and the efficiency of how fast you can solve this problem basically equivalent to the efficiency of how you solve this problem in Cat0 group. So, and again, in the cases where the answers to this question are known, they're all sort of based on some kind of non-positive curvature geometry. So that's why, which leads to this sort of a non-positive curved conjecture that probably all the Artin group are non-positive curved in some sense, and this may be one approach to solve this word problem conjugation problem of K-1 conjecture. That's sort of the one thing people have in mind. And there's also other motivations come from whether the group trying to define boundaries of the group or show some rigidity properties of the Artin group, which also relies on a certain form of non-positive curvature. Okay. So now this sort of the motivation, and I'm going to give you a more concrete example for at least for one of these motivations. So apologize for the moment because things are a bit abstract at the moment. So okay, so now I want to make more precise what I mean by Artin group are non-positive curved. So basically one precise formulation is that each Artin group is going to be acting geometrically on a metric space, which is a non-positive curve in some sense. So geometrically means the following. So it means the action is first properly discontinuous. Second, the action is co-compact. That means X mod G is compact. And then we want the action to be by isometries. So this is the meaning of geometric action. And the simplest example to have in mind is that if I choose a finite generating set, then the group acting on the Helly graph is going to be geometric. And the game we want to play is that I could start with some Helly graph, and then I begin to add some meat to the Helly graph, add some higher dimensional cells. And then in the hope that after adding some meat, then the space is going to be, I'm going to create a metric space which are non-positive curved in some sense. And that's the kind of thing I want to do. Okay, so basically I want to start with some kind of Helly graph and add meat to make it non-positive curved in some sense. And then, so now I want to say more precisely what I mean by non-positive curvature for metric space. There are many forms of non-positive curvature. So I want to start with one basic form. Some of you may already familiar with. So this is going to be what I'm trying to generalize in this talk. So first I want to define Cat0. So I take a metric space and let's assume the metric space is geodesic. That means every 2 points are joined by geodesic. And we define a metric space to be Cat0 if the triangles in X are thinner than that comparison triangle in Euclidean plane. So what do I mean? So first, a triangle in X is just I pick 3-point PQR and join them by some geodesic. So this is what I mean by a triangle in X. And for each triangle in X, I can draw a comparison triangle in the Euclidean plane. It means that the distance between P bar, Q bar, so now this triangle P bar, Q bar, R bar is in the Euclidean plane. I want the 3 sides of this triangle equal to the 3 sides of that triangle in X. So this is always possible because the triangle inequality holds true in X. So we should always be able to find such a triangle P bar, Q bar, R bar in the Euclidean plane. So now I'm going to take 2-point X and Y in the triangle inside X. And then we can draw 2 comparison point X bar, Y bar in the triangle in the Euclidean space. Basically, we require the distance between P bar, X bar is equal to the distance between PX, and distance between P bar, Y bar is equal to distance between PY. And then by saying that this triangle is thinner than that triangle, the condition I want to require is that the distance between X and Y is always less equal than the distance between X bar, Y bar, no matter what kind of triangle you pick and what kind of X, Y you pick in a triangle. Okay, so this is the definition of cat0. It's basically sort of a very intuitive definition saying a way of saying that metric space are non-positive curve. Okay. And then so the example would include that the simply connected Riemannian manifold with curvature less equal than 0. They are cat0. And all the trees are cat0 because if you think about what's a triangle in tree, they're tripod, right? They're thinner than the thinnest triangle in the world. Yeah. And another configuration to have in mind is the following. So let's take a collection of flat triangles. So each of the triangle is going to be some triangle in the Euclidean plane equipped with their flat metric. And I'm going to glue them cyclically around one vertex. And that's going to give me some metric space. And then, so it turns out that this metric space is cat0 if and only if you go around this central point and you look at the summation of the angles. We want the summation of these angles to be bigger than 2 pi. Okay. So this is another basic configuration to have in mind. Okay. Any questions so far?
Don't think so.
Okay, so now I'm going to move on. So so now this will be so now I want to show you a class of space where it's actually very easy to determine whether it's cat0 or not. So which is basically a cube complex. So I'm gonna, by cube complex I mean that it's gonna be I glue Euclidean cubes isometric along their faces. So the cube complex is going to have a natural metric. And then a typical example of a cube complex which is not cat0 is the following configuration. So it is made of 3 squares glued around a vertex. So now you see that if I go around this vertex in the middle, then the summation of the angle is really less than 2 pi. So that's going to violate this criterion. So for cat0, I want the summation of the angle is going to be bigger than 2 pi. Okay. And then I'm going to call this kind of configuration a missing corner because I'm imagine that there's a 3 cube. This is the corner of the 3 cube, but the 3 cube is missing. And then, so there's a nice observation by Gromov. It basically says that this is more or less the only obstruction to cat0ness for cube complex. So basically, if a cube complex has no missing corner and is simply connected, then the cube complex is cat0. So I'm being a bit sloppy here. So have no missing corner. First, this is basically a 2-dimensional missing corner, right? And you can define analogs for doing by 3-dimensional missing corner or 4-dimensional missing corner. So Gromov basically requires that you don't have missing corner of any dimension, then and simply connected. Then the cube complex is going to be cat0. And actually, so we can say a bit more. So if I give you a cube complex, a simply connected cube complex, which is not cat0, then what you can do is you can try to embed into a cat0 cube complex by keep feeding corners. whenever you see an empty corner, then you put a cube over there. And then but this procedure is generally not so good because when you fill in one corner, then you create another corner, and then you might have to keep doing this. So in the end, you might get something which is infinite dimensional, and the embedding from x to x prime may not respect the metric. So you could start with something x which is unbounded, and in the end you get something sort of distort the metric or not. Okay. But this turns out to be not the case for a class, very nice class for Artin group, which is called a right-angled Artin group. So let's try to apply this sort of filling corner procedure to a particular group. So a right-angled Artin group is an Artin group where all its relators are commutators. So this sort of the simplest class of Artin group. So we don't see this Braid relator. The only kind of relator we see are this kind of commutators. Okay, and then for the right-angled Artin group, so we can start with the presentation complex. So basically, that's a complex whose fundamental group is the right-angled Artin group. So the one skeleton is a variety of circles, one generator for each circle. And then I'm going to attach cells which correspond to the relators. In this case, I'm going to attach a bunch of squares. And now I pass the universal cover. The universal cover is going to be a two-dimensional cube complex. And then, so now I have a cube complex, I can try to, so what I mean is that whenever you see a two skeleton of a 3 cube, I fill in a 3 cube. And whenever you see a three skeleton of a 4 cube, I'm filling a 4 cube, and keep doing this. And then it's a nice observation by Charlie Davis that this procedure actually stops after finite step. So you don't need to keep filling corner. And then as a consequence of that, so each right-angled Artin group is going to act in geometry on a Cat0 cube complex. The point is that to make sure that the action is geometric, we want to make sure that we're not in a situation that we're forced to fill in corners over and over again. Okay. Okay, so this would be one example where you basically, so here we basically start with the one skeleton, and then I fill in squares corresponding to relators, and I fill in higher dimensional cubes, and I add in some meat, and then I get a nice non-positive curved metric space where the Artin group acts geometrically. Okay. So now the main theorem I want to state today is sort of a generalization of this earlier theorem of Charlie Davis to much larger class of Artin groups. So one of the main theorem we prove is that the Artin group type FC, they're going to act in geometry on some non-positive curved metric space. Okay, so now I want to explain what I mean by type FC. So this is a technical condition. So first I explain that an Artin group, I define Artin group is spherical if its coxet group is finite. For example, all the Braid group are spherical Artin group because the coxet group associated with the Braid group is this permutation group, as we've seen before. And then another sort of example is Zn is also Artin group, and the corresponding coxet group is basically a direct sum of Z mod to Z. That's also a finite coxet group. So basically, if you take Artin group whose coxet group is finite, then that's called a spherical Artin group. And what are the Artin group type FC? So okay, so definition is a bit technical, but I want to just mention what it really says. It basically says that Artin group type FC is basically you take a spherical Artin group and glue them in some nice way. Then you got the Artin group type FC. And the rigorous definition is the following. So okay, so let's say if I give you a graph, so the defining graph of the Artin group, and then it requires that for each complete subgraph, I take a complete subgraph, and then that's also going to define a sub-Artin group. I want that Artin group to be spherical. Okay, so the way to think about it is that so if I give you a graph, I can view the graph as a kind of a union of complete subgraph. And for each complete subgraph, I have a spherical Artin group. And then, so somehow I can sort of migrate this spherical subgroup together according to the pattern of how this complete subgraph sitting inside my big graph. So this is basically the definition of type FC Artin group. And then there's another theorem we prove is Garside group finite type acting geometrically on a non-positive curved metric space. So the definition of a Garside group is quite technical, so I won't get into that, but I want to give you some examples. So basically the main example is basically those fundamental groups of a certain hyperplane complement. As we've seen before, in the definition of Artin group, so we usually take some cones and then remove a collection of hyperplanes, and then we look at the fundamental group of the complement. And then so you can basically ask sort of more general question. If I give you CM and I'm removing a collection of codimension, complex codimension one, but real codimension two hyperplanes, and then what can you say about the fundamental group of a complement? And it turns out that many of the fundamental group of this complement, they have a structure which is similar to a Braid group, and this structure was axomized as a Garside structure, and that's how the Garside group come from. And these are the examples of fundamental group of complexity, complement of complexified finite visual arrangement. And that's also a certain class of complex reflection group that they also give rise to arrangement of hyperplanes, and you can consider the fundamental group of that complement. And it also arises as the structural group of some Yang-Basta equation. Okay, so these are the main results, and I want to say some immediate consequences. So basically, the main result says this group are non-positive curve in some sense. I haven't defined in what sense is non-positive curve, so I'm going to define that later. And then we can combine with this with some. There's a lot of work about non-positive curvature. What kind of property should a group satisfy if you know the group is non-positive curve in some sense, and then we get many consequences. So first I have algorithmic consequence. So we have so-called conjugation problem and the correcting function, which also implies so-called word problem for all these groups. And then we also have bi-automaticity, which for all the Artin group type FC. And there's also some topological consequence. So it admits an easy boundary. So that's some kind of very nice compactification of the group. And then we also have the Ferrier-Jones conjecture and the corresponding conjecture holds for these groups. And there's also some geometric consequence, like you can deduce that the higher order homological Dehn function is behaved like what you see in the Euclidean space, and it has a T's boundary. Okay. And then most of these results are actually new, although for example, there are some of these results are known before. For example, the Garside group is bi-automatic, so that was some result known before, but Artin group type FC are bi-automatic is not known. Okay, so now I want to go back to the main part of this talk. Is going to explain how we build a non-positive curved space for the action of a Artin group type FC or Garside group. Okay. So now I'm going to just focus on one particular example, which is the Braid group 4 strand. So basically what I want to do is basically something similar to what we did before. So we start with the one scanning time. We'll start with some kind of Helly graph and then add some beat to make it non-positive curved in some sense. And then so now I want to explain what is the thing I want to start with. Okay, so I take this Braid group and then I have the associated Coxer group. It's basically the same generator and the same relator, but I add this a square equal to b square equal to c square equal to 1. Okay, so that's just the permutation group of 4 strand, permutation group for letters. So we know that there is a map from B4 to S4. It's just a quotient map. And then so interestingly, this map actually has some kind of inverse. So we can define a map from S4. There's a canonical map from S4 to B4. Okay, this map is not a group. It's not a group homomorphism. It's just a map. but it's canonical in some sense, which is defined as follows. So I take an element in S4. And then, so since S4 is general ABC, so I can write this element as a reduced word in the monoid. So here I don't need to use inverse because A equal to A inverse, so A squared equal to 1. Okay, so that means I can write an element as a word in the monoid. We say this word is reduced, means that this word has the shortest possible length. Okay, and then so now I take an element in S4, I write it a word in terms of ABC, then I can treat this, because B4 and S4 has the same generator, I can treat G as an element in B4, and then this will give us a map from an element in S4 to B4. And we need to justify that this map is well defined. So because I take a word in S4, then you could written as many different ways as reduced word. And then it turned out that there was a classical result that if you take an element in S4 and write as two different reduced words in the monoid, then they differ by a Braid relation or a commutator relation like this. So that means this map is actually well defined. So you take two different representative as a reduced word, then they will give you the same element in the Braid group. Okay, so this is the definition of this section from S4 to B4. Okay. And then so now the way we want to think is that we want to think this B4 as sort of a union of this left translation of S4. So we call this left translation as apartment in B4. Okay, and then now we're going to define a complex called Savati complex. So okay, the 0 skeleton is going to be B4, and the 1 skeleton is going to be the Helly graph of B4 respect to this presentation. And the 2 skeleton is going to be, I'm going to fill in the 2 cells corresponding to the relators. And then what are the 3 skeletons? So that's the most interesting part. So this actually uses this as force. Okay, so first the 3 skeleton is going to be this this kind of pyramidahedron. So these are the 3 cells. Where does it come from? So basically come from that. Let's consider the S4 acting on R3, and then so I take a generic point, and then look at its orbit, and then take the convex hull of the orbit, and that's going to give me this 3-dimensional polyhedron called the pyramidahedron. And basically the one skeleton of the pyramidahedron is going to be the Helly graph of S4. So now let's go back to the set theoretical map from S4 to B4. So this set theoretical map actually also can extend to a map from the Helly graph of S4 to the Helly graph of B4. And you can even extend a little bit more to the Helly complex of S4, to the Helly complex of B4. And the Helly complex of S4 is basically looks like the boundary of this 3 cells. And then so now the 3 cells in the Savati complex, basically whenever we see this kind of apartment come from a translation of this S4. And then we're going to fill in a 3-dimensional cell. Looks like this. Okay, so is this super clear?
More or less, I think.
Okay. So basically, there's a 1-to-1 correspondence between the three cells and this translations of this copies of S4 in B4. And this cells looks like this. Okay. So now this is the Savati complex I want to work with, and then so now I want to so my goal is to extract some non-positive curvature feature from this complex. So basically the key point is I want to try to see how, so I have a lot of this, so the Savati complex is the union of these 3 cells, and they intersect in each other in in an interesting way. What I want to say is that they intersect each other in a non-positively curved pattern. Okay, so now I want to define what do I mean exactly. So basically, this definition was designed to describe how these three cells intersect in the Savati complex. So okay, so I take a combinatorial cell complex such that each closed cell is embedded and full. So this is just some technical condition. You can ignore it. So I want to define X is cell Helly if the following is true. So the first, any intersection of cell is either empty or connected and simply connected. So this is a standard assumption. So the first one is not the most important one. The second one is basically says that the finite cell has finite Helly property. So that means any non-empty pairwise intersecting implies non-empty intersection. So if I have a collection of cell which pairwise intersect non-emptily, then the intersection of all of them is non-empty. So this is the kind of condition which allow you to work with the nerve. Okay, and then the third condition is the most interesting condition. So that's where the non-positive curvature came from. So it basically says that if I have a three cell C1, C2, 3, they pairwise intersect, then I claim that there exists another cell which contain the union of the double intersection. Okay, so this condition is a bit mysterious, but it's going to be easy once we look at this picture. So let's think about what does it mean in a cube complex. So I want to say, okay, so let's suppose we have this missing corner as before. So let's say I have C1 is a square, C2 is a square, C3 is a square, and then so this three cell pairwise intersect. And then what is C1 intersects C2? C1 intersects C2 is this 9, C2 is intersects C3 is this 9, C3 intersects C1 is that 9. Okay, so basically, I basically says that I want which contain these 3, 9. So this is basically one way of saying that the corner formed by the cell C1, C2, and C3 is filled by this another cell C. Okay, so this is basically the geometric way to think about this. So the left side is, you can think about some kind of corner, and then this right side C is basically I want some cell to fill in this corner. Okay, so the intuition sort of come from this Cat0 cube complex. Okay. Okay, so now let's go on. So this is a sort of a combinatorial version of non-positive curvature, and it's also quite local, and it's actually a bit hard to work with this directly. So basically, in the end, we show that this Savati complex, they are cell Helly in the sense of this definition. And then, but this is still sort of further away from what we really want for non-positive curvature, because if we think about definition of Cat0, it's sort of a continuous version of non-positive curvature, and it's a global notion of non-positive curvature, and it basically tells you no matter how large is your triangle, then you can always compare it, right? So that means our next goal is I want to start from this cell Helly, which is the local version of non-positive curvature, and which is also a combinatorial notion of non-positive curvature. And I want to start with this non-positive form of non-positive curvature to pass to a form of non-positive curvature, which I call convex geodesic bicomplete, which is a global version of non-positive curvature, and which is also a continuous version of non-positive curvature, which is easier to work with. So now this passes through several stages. So I'm going to explain now. So basically, to summarize, we want to go from local to global, and we also want to go from combinatorial to a continuous setting. Okay, so the first is I'm going to explain this process of thickening. Okay, so to thicken to a Helly graph, so I need to explain what is a Helly graph. So first, I want to define the notion of hyperconvex. So I take X to be a geodesic metric space. We say X is a hyperconvex metric space if the collection of closed metric balls is a Helly family. So that means if I have a collection of balls which pairwise intersect, then the intersection of all of them is non-empty. The example you have in mind is in the trees, this is true. So the balls subtrees, if you have a family of subtrees which pairwise intersect, they indeed intersect. And then another example you have in mind is the L infinity space. So you can just think about R2 with the L infinity space, R2 with L infinity metric. Then the closed metric balls in R2 are basically boxes or rectangles. And if you have a collection of rectangle in R2 pairwise intersect, then they actually has a common intersection. Okay, so these are the two basic examples you have in mind. And then, so now what are Helly graph? Helly graph are basically graph theoretical analog of hyperconvex metric space. So basically, you can also define, instead of consider closed metric ball, we can define combinatorial ball. It's basically it's a collection of vertices which has distance lesser than n from a given vertex. And then you can impose the same condition that you require that this combinatorial balls, if they pairwise intersect, then they have a non-empty common intersection. Okay, so this is what I mean by Helly graph. It's basically a combinatorial graph theoretical analog of this hyperconvex metric space. So now, okay, so now I want to connect from cell Helly to Helly graph. So basically, the procedure is the following. I take a cell complex and I define something which I call a thickening. So basically, the thickening of this cell complex is a graph. The vertex set is basically made of the vertices of X. And then we claim that two vertices are joined by an edge if they're in the same cell. So it's basically I'm collapse each cell into a simplex, if you like. So or into a complete graph. Okay. So this is the thickening. And then we have the following theorem with Osajda. So basically, it says that if I have a locally finite simply connected cell Helly complex, then the thickening of this is going to be a Helly graph. Okay, so this is really what we're really going on here is a local to global theorem. So because this a cell Helly complex is a local condition. But this Helly graph is a global condition because it is required that the intersection of these balls, no matter how large is this ball, is going to satisfy this Helly property. So this Helly graph is a local, is a global condition. And then, so this theorem is kind of an analog of the Cartan-Hartman theorem. It's basically you have some local version of nonpositive curvature, and then you have simply connect this. Then that's going to lead to a global version of nonpositive curvature, and that's really what's going on in this theorem. Okay, and then as a consequence of that, if I have a group acting geometrically on a simply connected cell Helly complex, then it's going to act geometrically on a Helly graph. So now from the moment, so I know that this Artin type of C and the Garside group, so they satisfy this. They're acting on some complex of the cell Helly. Then from the theorem, we know that they're acting geometrically on some Helly graph. Okay, so this is the first step, is from local to global. And then the second step is I want to add some, I want to go from sort of this combinatorial or discrete setting to a continuous setting. So this is the second step, which I'm going to take some kind of whole. Okay, so now there's a classical theorem by Isabelle that every metric space is going to be isometrically embedded into a canonical minimal hyperconvex metric space. It's called the injective whole. So the construction of this, but in general, the problem is that this injective whole could be much bigger than the metric space you start with. And then the upshot here is that basically we want to say that if I start with a Helly graph, and I take the injective hole, then the injective hole won't be much bigger. And this actually already follows from some previous work of other people. So it basically says that I take the Helly graph and I take the zero skeleton. So, and this is going to be, this is a metric space if you consider the induced path metric on the zero skeleton. And I can apply this whole construction of Isabelle. And what they show is that, what they showed is that the injective hole is actually at a finite host of distance from the metric space you start with. Okay. And we also know that the injective hole is proper if I start with a graph which is proper. Okay, so in this case it just means locally finite. Okay. And then so from this I know that if I have a group acting geometrically on a Helly graph, then it's also going to acting geometrically on a hyperconvex metric space. Okay. Okay, so now we have this sort of continuous metric space which is hyperconvex, and I want to explain that this hyperconvex metric space indeed have some feature of nonpositive curvature. So one way to see that is the following. So okay, so we're going to define a notion called geodesic bicomponent on a metric space. So which basically is the following set of information. So a geodesic bicomponent is basically for every pair of points. Let's say I take a pair of points X and Y in my big metric space, big X, then I'm going to assign a constant speed geodesic from X to Y. So basically, bicomponent is just a sign of a geodesic for every pair X and Y. So I'm going to assign a geodesic from X to Y. So a priori, I'm not saying that the geodesic from X to Y is equal to the same as the geodesic from Y to X. So that's the next thing I want to require. So we say this component is reversible if basically this basically says the geodesic from X to Y as a set is the geodesic from Y to X. And then we say the components by consistent if basically it says the following. So suppose I have a geodesic from X to Y, and then I have 2 points P and Q lies in this geodesic. And then the consistent requires that the geodesic from P to Q is contained in the geodesic from X to Y. So this is also a fairly natural condition. Okay. And then the last thing I want this geodesic component to be convex. So basically, let's say I have 2 geodesic, one from X to Y and another one from X prime and Y to Y prime. Let's imagine that I'm moving on the first geodesic, and let's say it's parameterized by T, and I also moving on the second geodesic, which is also parameterized by T, so constant speed. And then I want to consider this function from T to this distance. And then the third condition requires that this function is convex. So this is actually you can understand the third condition is a weak form of nonpositive curvature. For example, if the third condition is going to be true if you if you are in a Euclidean space. So if you are in Euclidean space, you have 2 geodesics and you work on the 2 geodesics, and then this function is going to be convex. And this also holds true for Cat0 space. So if you have two geodesic segments in the Cat0 space, you move sort of along these 2 geodesics, and then this function is also going to be convex. And then this is sort of a way of saying that your distance function has some version of convexity. Okay, so that's one way of saying nonpositive curvature. Okay, so now then we can. I want to mention the following theorem by Nang and one of his students. So that basically shows that if a geodesic hyperconvex metric space has to satisfy a technical condition which they call the finite combinatorial dimension. They're going to have a unique geodesic puncturing which is consistent, reversible, and convex. Okay, so the example again, the example to have in mind is that you can think about the I infinity space. So the I infinity space, okay, so what is the most natural geodesic bicompany you want to assign? So because it has a linear structure, so if I give you 2 points, then you just connect them by the straight line. Okay, so that's going to be sort of the geodesic bicompany in that setting. And for general hyperconvex matrix space, what they do is that they're going to embed that into some linear space. And in the linear space, there is a natural bicompany, and then they somehow retract back to the space to induce a bicompany of the matrix space. So I'm denying that, but it's sort of the idea. Okay, so now by putting all this together, then this is what we get. So basically, if I take a group which is either a Garside group of finite type or an Artin group of type FC, then in the end, so we have a group acting geometrically on a hyperconvex matrix space. And hence, since the hyperconvex matrix space is a matrix space with convex geodesic bicompany, so we know that any such group is going to act in geometrically on a matrix space with a convex geodesic bicompany. Okay, and we also know a bit more. So this space is actually has a polyhedral structure. So this is basically a piecewise. It's basically made of polyhedrons lies inside some finite dimensional L infinity space, and then we basically this space is basically we glue this L infinity polyhedral together. Okay, so this is the space I wanted to describe, well, which is acting geometrically by a Garside group or Artin group type FC. And I think it's time for me to stop. And thank you very much for your attention.
Thank you, Jingyin, for your talk. It was very interesting. So, do you have any questions for Jingyin? Well, it seems like we don't have any questions, so let's thank Jingyin one more time.
Thank you.
And yeah, now we have a break for coffee, tea, beer, whatever is appropriate.